So welcome to this third lecture, core lecture on autonomy. So what I actually want to do today is first talk about sequence generation. That will be the main new contents. I have a brief discussion about neural architectures. Why do DFT architectures actually work? To reflect a little bit about that. That helps also with the embedding of DFT in the theoretical landscape. So I promised on the first day that I would come back to knowledge that some of you might already have. And so I'll discuss a little bit the relationship between DFT and, for instance, classical cognitive architectures, connectionism, and spiking neural networks, VSA, vector-symbolic-architectures, things like that. And there will be also an opportunity for us to discuss a little bit more than we have. That's the plan. So sequences. And I emphasized already in the first two core lectures that a lot of the things that we were looking at actually involve sequences. You saw that these cognitive architectures that did grounding go through multiple steps. We even looked at an example of hypothesis testing where the system was first selecting one object and then discards that object and selects another object. And my claim was that all of this happens autonomously. That's where the title comes from of today's lecture, autonomous, that is driven from within that system by its own resources, not paced externally by stimuli and certainly not by a computer clock that says at a certain time you load something into a processor and so on. And I think it's a moment's reflection, and a psychology textbook will reveal that pretty much everything we do consists of sequences of individual acts, mental acts, physical acts, elementary movements, movement acts, chain together make our behavior, and mental acts chain together make our thinking, our speaking, our listening, our attending, and so on. All of these are sequences. And that's, of course, one of the reasons why people have thought of cognition as a form of computation, took from the computer metaphor that idea that a computer has a clock and operates on instructions one after another and so on. And has not really thinking very deeply about exactly how that happens in time in this wet thing that we have up there that's called the brain. So there are a few cases where these sequences are really fixed and rigid. These would be skills. I mean, when you grasp a glass, you don't think about, oh, extend a hand and now begin to draw in the fingers, right? So there are some fixed sequential actions, highly trained patterns are like that. But in many cases, of course, that these sequences are very flexible. In language, that would be the most extreme. Presumably, I'm not saying the exact same thing I said before. In my case, you might have some doubts about that. But in general, of course, we assemble sequences of thoughts and of actions and of words that are very variable. This is this property that's sometimes called productivity in cognitive science, that you're able to make arbitrarily many, sometimes even a question if it's really infinite or not, different kinds of sequences. And in behavior, that's certainly true. Okay, so it's very important to understand how sequences work. Now, we want to understand, of course, how sequences work in neural terms, right? In neural processing terms, and we use DFT for that, as contrasted to just assuming that there is something, that can call a subroutine and then returns control on a computer, right? And so when we do this neurally in DFT, then we're dealing with attractor states. We're hypothesizing that the neural states that are instrumental in bringing about a particular behavior or a particular mental process are governed by neural dynamics that have attractor states. And we have these arguments that that's necessary ultimately for linking these processes up to the sensory motor surface. And attractor states resist change, right? And in a sequence, you're changing state from one step to the next, right? So there is a conflict between these two constraints, to change and to resist change. And the answer, of course, will be that we will have to give up stability to enable change. So we'll have to induce instabilities in a targeted way. And you're familiar from the previous lectures with the candidate instabilities that we can use. So we'll use instabilities to selectively and systematically destabilize the state that we want to end, and then enable reaching a new state that will be the next step. And I'll take you through an example for that, and then I'll talk a little bit about the general mathematical idea behind that. I'm not doing that very abstractly. So this example is a physical example of a sequence of physical acts. It's actually a form of visual search, but for an agent that moves around an environment. In the experiment, it's actually a little robot that uses the kind of dynamics that I present in the first lecture, and it avoids obstacles, and that makes it actually, I didn't explain how that works, but it's also a very simple thing. And as a result, it meanders around the environment, and in this environment, there will be objects of different colors. Again, we always use the very simple feature values. And the task of the vehicle will be to visit these objects or search for these objects in a particular order in terms of the color. That is, first find a blue one, then a red one, and the third, I'm missing here, the number 3, then find a green one, for instance. And that is will take variable amounts of time. This vehicle doesn't have a real map of the environment, so it will have to search and takes time. And so we're this is designed to exactly probe that problem that you want to have stability to achieve your goal. So you don't want to, for instance, go to the red object just because you happen to pass by a red object. So when you go by a red object and that's not your current goal, then you don't want to destabilize your red. You want to keep your red intention going. And then, but then at some later point when you have achieved red, then you should be open, for instance, to go to a green object. So the concrete implementation of this was the topic of Julia Sandomierska's doctoral dissertation published in 2010. And she had actually a scenario in which she did both things autonomously, that is defining the sequence and then acting out the sequence. So the defining was based on learning. She was actually here showing to this little robot, the camera is pointing in the direction of her hand, showing it objects of a certain color in a certain order. I think it's yellow now, red, and then she's showing the robot green, blue, and again red. And there's a little subtlety you see at the end of showing a cube, she moves it a little closer to the camera. That actually indicates to the robot that this step is finished and it should learn the next one. I'll show you how that works in a moment. And then she sets up this arena. Right? I didn't film that, but she sets it up in a new form. So this robot doesn't know about any of the spatial layout, and the robot just wanders around avoiding obstacles more or less. And as a result, it somewhat samples the scene. So it actually approached the yellow. So it's programmed to, when it finds an object on its sensory surface, it actually moves there until it's really large on the sensory surface. And then it's done and moves somewhere else. And it will, for instance, I don't know what it's actually currently looking for. So we'll solve this task. And I wanted to show you here on the next slide, particular contrast. So this is the robot passing by the red when it was actually looking for some other color. And so it was ignoring the red. Well, this is somewhere later in the sequence when the robot is actually really aiming at red. And then it drives close to red and then actually moves on as it switches. So this sort of demonstrates that the system can be selectively attentive to what is current task, stabilize that task, and ignore distractors. And then only when the task is done will it be again open to objects of that other kind of color. So the core idea that we invented around that time that has since become a real cornerstone of DFT. You see in the book, it's actually the second to last chapter. So it sort of was the most advanced for some time, but now we've moved way beyond that. We use this everywhere. So this idea is what we call the condition of satisfaction. The term was actually adopted from John Searle's theory of intentionality. And there's a project that Jan Tekulve actually did his PhD thesis on to really push that. And he will talk about that on Friday, push that analogy to intentionality. So here, this was, I'll just take that word for now, and we'll see more about that later. So the idea of that is that when you have a certain action plan. Here we call that actually an intention to find, let's say, a green object. That action plan makes a prediction about what the sensory outcome of realizing that action plan would be. That's this little arrow makes a prediction, and that prediction activates a neural representation we call the condition of satisfaction. It's a neural representation of that. That prediction alone is not enough to induce a peak, but then you have, act out the action, you have some way of realizing that goal, and then you get some visual information in this case, or sensory information, and that percept would provide input to the condition of satisfaction. And if it matches this prediction, so where the peaks overlap, for instance, so the inputs overlap, then a peak is generated in the condition of satisfaction field, and that would be then the trigger of an instability. It would actually inhibit, here it goes to another layer, I'll explain that later, but ultimately what it does, it inhibits this peak, and therefore ends that state. So inhibits means you go through the reverse detection instability, and then in fact what will happen is that because there's no peak anymore, there's no prediction, and then also this year will decay. Before I go into the math details of that, let me illustrate that for you. So this system is actually doing a form of visual search that you're familiar with now. It is a one-dimensional search in one-dimensional space, because we're only interested in the angular dimension, so the direction, for heading direction, right? And therefore we're summing actually all the inputs along a vertical column, and what we're doing is actually computing a color histogram. So over color, we're looking how many entries there are at different hue values. For instance, if you look at this element here, you will get a lot of white, which will not contribute to the hue space, and then you'll have a lot of entries in yellow, and that will give a nice peak in yellow. And so that's the sensory information you get about color, and visual search will essentially erect a ramp, a ridge-like input at the search color. For instance, if it was yellow, it would be a ridge along the color dimension localized at yellow, and homogeneous along space that would be overlaid with the kinds of inputs I just showed you. So the different spatial orientations, so the different columns in the visual array of the camera. You have this histogram across color. So this peak here would be, or this input here would be the result of an input like that. That's how the visual search is realized on that vehicle. So it's not making eye movement, it's actually moving around, both turning and driving around. And that's the form of visual search. It's literally a search of a vehicle, random walking here. So here is sort of an overall summary of what happens here. So your intention, so we have the special case that the intention and the outcome are the same. That's like the trivial example we used to establish the idea. So here, your intention is to find a certain color, and your condition of satisfaction is to see that color, right? It's color to color, very simple. Of course, in general, this would be much more flexible. You could say maybe my intention is to grasp an object, and my visual feedback will be maybe to see the object in my hand, or to have some haptic input about that, or to have some proprioceptive information about tension in your muscles that you're exerting force on a surface and so on. So you would have multimodal and effects that will potentially be quite different from the shape that the motor intention takes, or the action intention takes. So we just took this trivial example to make things simple and easy to demonstrate. So the intention is a particular peak in an intention field at a particular color value that guides, as I just hinted, visual search. And in this visual search, there's constantly a chance to take any of these inputs. The different objects are 2D inputs into the color space field. Remember, we're just using one spatial dimension, the orientation dimension, so we're summing across the vertical. So these little peaks here are entries directly from the visual array. This would be 2D entries, bound in the sense I explained yesterday. And then through the ridge, I'm fishing out any localized peak of activation, fishing out any 2D input that overlaps with that cue. And then a peak forms. And when a peak forms, there's actually another behavior that isn't explained here. Then the system actually really, there's a peak generated in a target field, the heading direction is attracted to that, and the vehicle moves toward the object like that. That's how that peak will be, the visual object become large on the sensory array, and large means it extends along the vertical, and there will be a lot of entries into the histogram. So as a result, what happens is that ultimately there will be a lot of a large amplitude here in the input strength, and that supports this perceptual. So there's a graded measure of perception. So then you will get a large peak in this perceptual field. And that perceptual input is provided to the condition of satisfaction representation, which is pre-shaped or pre-activated by the intentional input. So this is the pre-activation, and now a peak hasn't formed yet here, but once enough input has been perceived here and that overlaps with this peak, then the condition of satisfaction generates a peak. I have some videos that I assembled from Julia that illustrate the time course of this, and there's a slight difference in the system, so I'm not explaining that. So here's an intention, for instance, that creates this ridge in the search field. The condition of satisfaction is here, just one neuron representing that entire field. And at some point here, yeah, I guess right now, a peak was formed and the condition of satisfaction fires. And actually here, it's separate fields or different intentions. So this first field was deleted and the next field was activated. I didn't explain how that happens. And so another search, actually there was another condition of satisfaction here. Again, this hasn't fired yet. This isn't large enough. See the inputs as the vehicle is walking around, there's some inputs walk around. And at some point, these inputs will overlap here enough with that ridge right now. And when that peak is large enough, it fires a condition of satisfaction, resetting and charging a new, so inhibiting and charging a new intentional states. So I'm showing this, some of the details here are different, like I didn't explain this here, the ordinal stack. But for you to get a sense that now really events happen, right? These events happen when a match is detected. And you see it's not equidistant, it takes a different amount of time to reach these different objects of the corresponding colors. Now, this is how now the system does sequential stuff, right? We make these events happen, and these events trigger changes in the system that then activate the next state, and that's based on making targeted instabilities. Here is a illustration of just one of those transitions. So here is the intention field. So there's a peak at whatever color that is, I don't remember. And there is some neuron that represents what, where you are in the sequence. I haven't explained that yet. And the condition of satisfaction is pre-activated. This is the yellow is sort of an intermediate level of activation, not yet a peak. While here, this red one is a real peak. And this is when the condition of satisfaction signal comes in. The peak is being formed here. That peak drives inhibition of these intentional systems, and that ultimately inhibits away the current intention. And then as that goes away, then the condition of satisfaction also decays. And then actually in this case, the next system here, the blue is the next node. I haven't explained yet how that works. The next blue node comes up, the previous one stays off, and the next color is loaded here into the intention. So in effect, this is how the system, this again, just from some run, shows here which intention is activated. It shows, I believe this is the condition of satisfaction, and this is something about where in the image the corresponding state is. And so the important point is that you see that the system is taking different amounts of time, and within these intervals, it is stably focused on its task, is looking for the expected color. And then when it condition of satisfaction fires, it is able to switch to the next task. So it shows the different orders that it does in. And actually during the learning stage, the same happens in the learning stage. And this is why Julia was actually moving the objects closer to the camera, because that would make the color peak large and would switch a condition of satisfaction. So it's a learning mode in which it's not a where it's really just the condition of satisfaction is really just triggered by a large monocolor peak in the perceptual field. And then the next node is open to learning. It's actually learning through having learning what color is associated with the next step. And again, this association and how to select the next one, I will explain a little later. In her learning trials, it's a bit more rhythmic because you're sort of presenting this as somewhat of a rhythm, but it's not precisely rhythmic. So sometimes she held it a little longer, sometimes less long. So that's the main feature, this ability to have stable states as long as required and only then move on, right? So if you think of other ways of doing this, where you would have some kind of schedule, a lot of models of serial order, for instance, were based on that, an idea that one neuron triggers the next. And that works if you have just transients in the brain and in a network, for instance, a famous model has that, one population is the next on chaining system. And that only works if it's not connected to anything real, or these processes are all the same. They all take the same amount of time. And we do a lot of sequential things rhythmically if we can, but it's quite critical that we don't always do that. Playing the piano would be very boring if you had to make all the intervals exactly the same, right? Good, so that's illustrates most of the ideas. And essentially what we are doing in general is we're doing the same sort of thing when we're making a purely mental sequence, when it's not physical. So what the general mathematical mechanism is summarized here. So what I just showed you, you have some representation of what your intention is. That could be a motor intention, or it could be also an intention to create a particular mental state. For instance, when you do mental arithmetic, right, to create a step, or to the examples that we had where you try to enter something into memory. I'll show you an example from Jan's work a little later, where you see some peak is creating a work in memory, and that was the intentional act. And once you've done that, you can go on to the next item. Excuse me. So that's the intention that makes a prediction. This is a different dimension, y, and so that pre-shapes the activation. It will be like a below a peak. And then if you get a signal through the world, as the example I just showed you, through some perceptual state, that could then trigger a detection instability here that could create a peak. And because this field or node is inhibitorily coupled to this intention, it will, once there is a detection instability, it will create a reverse detection instability on this field. So this peak will go below 0. And therefore the prediction will fall away. And if you arrange things correctly, then if the prediction falls away, even in the presence of a suprastate, a suprathreshold input from this one, you can go push this through the reverse detection instability. So then both of these peaks are gone and you're done with that intention. And so which intention comes up next would be then decided by something that I'll discuss in a moment. So we showed the example where it goes through the world, but you could also really have a signal from some other neural representation. I'll show you an example later where you're looking at what happens in a target representation. That's not these two fields. This just is a text that explains what I just said. In some sense, this is related to what some of you might know as efference copy. Excuse me one more time. So the notion of efference copy is also an idea that if you have a motor command that you're predicting the sensor information that would be expected when that motor action is performed, and in the literature of this efference copy, so is sort of a more general concept than reafference. So you might have heard about the reafference principle. Goes back to von Holst and Mittelstadt. That the difference is it also acts inhibitorily, but in the general thought of efference copy thinking, the inhibitory effect is on a perceptual representation. That is, you're not perceiving perceptual effects that are caused by your movement, so that are not surprising in some sense. And so that's related. Here we're looking at inhibitor, in fact, on the motor intention. And it's not excluded that some of the cases where people talked about reafferents were actually including a motor component. I think it would be interesting to look back at some of that literature in that light, but it's not always been studied, of course, in that way. So it might be related to this idea of reafferents or efferents copy. So a lot of the examples that I showed you yesterday contain ideas like that. Is somewhere in there was a subpopulation of the architecture that acted as a condition of satisfaction, that is, that inhibited the originating state when it was activated, and its activation was conditional on some component of prediction from the intention. So it's not always that explicitly there's one field of one nature and another field of another nature. It's more the neural principle that that the sketch here is supposed to illustrate, and it is realized in different architectures in different forms. So, for instance, in some of our architectures, we're now using a more sophisticated form of that, a sort of general principle of mismatch or change detection. And in the book, there is a chapter on change detection, which I believe is maybe chapter 6. And this here is actually a generalization of that. So I'll not explain that in a lot of detail, just to say, this will be an example where you have two things to match. For instance, you're attending to a certain feature and you have a prediction about what feature you get. And then you could have, for instance, a match field, so that when these two are at the same place, a peak would be, actually this is a mismatch field. So when these two are at the same place, then one is excitatory, the other is inhibitory, so it cancels. And so when they don't match, then they don't cancel, and one of them will create a peak, and then you can combine the peak detectors. There's some neural representation that is sensitive to whether there's a peak, in order to compute from that if there's a match or a non-match. And that's how you could, more generally compute a condition of satisfaction. And the interesting thing of that is you can also compute from this a condition of dissatisfaction. That is, you could detect that there is no, that the effect that you were aiming at did not come about. That is a well-known problem in cognitive psychology. So how do you know that there's a mismatch now? Maybe you didn't give it enough time. Like some of you know these little visual puzzles where find the difference, right, between two images, and you have found 8, but supposedly there are 10. How do you know that they're 10? You've tried forever and didn't find the 9th and the 10th. And ultimately, there's always some idea of some kind of timeout, some kind of stopping, that you give up at some point. And there's that is a question of how much time you give yourself. And that's actually implemented generically in these sort of things, in that there is a race, there is a default, no match response. So this response will win. It takes some time for this to reach threshold. And when it wins, it will inhibit the match response. No, it's actually the other way around, right? Sorry, the no match response. Yeah, the no match response wins by default, and the match response is then inhibited by the no match response, because the match response would be based on not noticing a difference, not having a change signal. So I'm not explaining that here in detail. In different models, this is used in different forms, and I don't think in our. So it was, for instance, relevant to this hypothesis testing story. There we had a condition of dissatisfaction. So this is something that requires a little bit more discussion. I'm just giving you the perspective that there is also that other element of the opposite of condition of satisfaction. Good. So this much about that mechanism. That mechanism is very much present everywhere in our architectures. That's what makes them do sequences of things. But I've only explained one aspect of that. I've explained that you're ending a current state by making it unstable. Now we have to think about, how do you then select the next state? How do you, determine what sequence to make. So one is to control it temporally, and the other is to make the selection. And that's where we're implementing ideas that are in the literature, three notions: gradient-based selection, chaining, and positional representation. I'll go through those. All three of those are used and realized in DFT, and I'll illustrate then these ideas in one integrated example. So this notion there's a review paper by Hansen and Burgess. I don't know how to pronounce this name. Is it Burgess or Burgess? In 1997. But I don't think that they invented these terms. I think these have been around for a very long time. I don't really know historically who was the first who came up with these different ideas. And so the three proposals, they weren't, of course, framed in neurodynamics, right? They were more abstractly framed in terms of some kind of abstract neural network kind of mechanisms. And there's a literature on finding behavioral evidence for these. I'll not go through all of that, but there are some arguments that all three might be realized under some conditions in very different kinds of tasks. So this is useful for serial order in perception, in thinking, but also in motor behavior. So I'll go through each in turn. So the gradient-based idea is that you have some activation patterns, for instance, could be a salience map or some input map and so on, in which different possible choices in our language will be localized in these fields. In other neural networks, maybe could be the individual neurons that stand for something, in which there's a different level of activation representing how close to you are to being selected. So you could encode the serial order in this level of activation. There are proposals, for instance, by Grossberg's group, that you could even engineer some special neural circuit that can store in working memory a level of activation. So a neuron firing a lot for the first and firing less for the second and less for the third. These are, again, there's some arguments that might exist. These are sometimes called line attractors. They are inherently not stable, marginally stable. It's not totally excluded that that could happen. I believe it is, if it happens, it's a very special kind of mechanism. It's much more commonly relevant for selection that's input driven. For instance, in our visual search system, after you're done with one entry, you will be selecting another one, and that other one would be the most salient other than the one you just had. It's actually that inhibition of return that we're using to delete the item you just looked at. Right? If you looked at this item previously have a representation in an inhibition of return field, it's a working memory of that, of having been there, that then inhibits that item. And so the next most salient item that has most input would be selected, right? So it's quite, that's a very common form of how this happens in the architectures. I showed in all three architectures, this is used somewhere. One could think of that as also being sort of very general kind of idea for mental activity, and it's actually in some less neurally realistic form. Even classical cognitive architectures use an idea like that, that is that you would have some form of competition between possible mental acts or mental operations, and they would get some, they would have an activation variable that represents whether they are being executed or not, and that when you're selecting your next one, you're adding all the inputs that they get, all the votes for each activity, and then you would select the one with the most votes. So you could think of, when I'm speaking, I'm maybe context and thought and some linguistic rules and so on would all pre-activate certain things I could say, and then one of those will win. And that will be gradient based on that. The one that wins is the one that gets most inputs, for instance. So that's a very general idea. Chaining is a bit much more specific kind of idea. And there is actually reasonable evidence for chaining in sort of fixed sequences that you have learned. And so what the idea in chaining would be that there is some kind of directional coupling, so that one node would be when it's active, it would pre-activate a subsequent node, and when you have somehow arranged that's not accounted for in the classical thinking for the previous node to go off, then the next node is activated because it was biased by this directional coupling. So, so that as a general idea is less flexible, you can imagine. You know, if you have chaining, the main difficulty of chaining is that you have to do some special gymnastics if you have a sequence in which one thing happens twice. For instance, the example I just showed you, there were maybe, I think there were maybe red objects in two positions in the serial order, and therefore you would have to represent that this is red in that first case followed by green, let's say, versus red followed by blue, because in the chaining idea, once you activate a particular behavior, then it uniquely points out what the successor behavior is. And so there wouldn't be a possibility to have two different successor behaviors. And there have been some proposals for workarounds, like having multiple copies of everything, but you can see that that might be a little bit more problematic. But there's some evidence for ideas like that when it comes to fixed action patterns, for instance. We're using this in some of our architectures exactly to explain cases where there's a systematic preference to perform certain things in certain orders. So for instance, in the relational architecture, we hypothesized a particular order in some cases. The neural way we do that is that we have, these are always pairs intention, conditional satisfaction nodes, and there would be this form of double inhibition. This is called a precondition neuron in our jargon. So when that precondition neuron is active, it is inhibiting the intentions it is projecting on. And this condition of satisfaction inhibits this precondition neuron. The precondition neuron is on by default. So when that is inhibited, it releases this downstream action from inhibition. So in that sense, when you're done with this one, the next one has a chance to become activated. And by having descending inputs, you can sort of select which intentions you pre-activate to be potentially activated, and then the chain sort of releases every node when its predecessor is done. So that's used in some of our robot, for instance, reaching activity, and a couple of systems like that, like in some of our action architectures, which we don't really explain here. There is, for instance, a fixed sequence that you have to first have an object selected potentially before you can make it a target of a reaching movement, right? Which is sort of logically unique in its serial order. You don't want to reach first and then select the object, right? It doesn't make sense. Good. Now, the most interesting one is the positional representation, which in a sense combines the chaining idea with a much more general idea of neurally representing the contents. So the contents of individual nodes is free. So there would be an idea that you have some form of chaining mechanism. We call this an ordinal representation. So some nodes which are arranged as one possible arrangement to provide a chaining mechanism. So for instance, in the sort of a generic form, there's multiple ways to realize that generic form. Each intentional node here activates a memory node. So this node will remain activated when its inducing intentional node is off. So for instance, when this node is on, it activates this memory node. And then when this goes off, the memory node stays on, and each memory node points to the successor intentional node. So this node on means this intentional node is a little bit activated. While this one is activated, it's not winning. This is globally inhibiting. But when this node is inhibited, or actually the whole system is inhibited and then released from inhibition, then this node has an advantage because it's activated from this node, and that will mean on the next step, this node gets activated. So this is a possible very simple form of chaining. And then the notion would be that what these nodes represent, that is learned. And this is how Julia did this. So for instance, when this node is active, it has synaptic connections to, for instance, certain color field or action field. And through Hebbian learning, it would associate its activation with this contents. And then you see this is much more flexible. You're pointing. You have a positional representation of the order. That's why we talk about ordinal nodes. It's sort of like a dimension, but it is sort of discrete in organization. And that can then learn any projection onto other feature dimensions. So this was at the core of one version of what I showed you. And there, these ordinal nodes were pointing at these action fields and each, to different locations. They were essentially becoming concept nodes through that. They were pointing to a condition of satisfaction field. In this case, this was very simple, but we also showed how you could learn conditions of satisfaction. And then the intention field was, driving the motor system, in some closed loop, and then also driving the condition of satisfaction perception, which would trigger here the detection of match. And when that happens, the whole ordinal system was inhibited, this intentional layer. And when that happens, this goes away, the peak goes away. And then when it's released from inhibition, because the condition of satisfaction goes away, then this will switch one to the right, one ordinal node on, because this will bias the selection. And when the inhibition is disappearing here, will bias this node to be selected. That's how that worked. So that's very flexible, and it's often been invoked as the most general principle of serial order. Serial order expresses that the ordering of items can be varied somewhat freely. There might be constraints like grammatical constraints that certain categories have to come in different places, but overall that you're able to assemble any sequence as long, consistent with some grammatical rules for action or for thinking or for language and so on. And so the system is also very good for learning because it's a very, very clear place where you put the learning here into these connections. And the other two, that's a little less obvious. The limitations of this are clearly that if you think about this as learning, then of course you have to have the projections, right? There must be some substrate for that. So these neurons must be projected to something. And it could be a problem if you have some neurons that are selected to just about anything in the brain. There is actually a serious talk about systems like that in hippocampus. And one of my colleagues here in Bochum has a hypothesis that something like that is at the basis of the so-called pre-play feature. Then you have hippocampal activation that is observed, for instance, when a rat navigates in a lab, and there's what is called replay, where you see that same sequence of activation hippocampus when the animal is sleeping, is dreaming. It can be sometimes backward, sometimes forward. And there's also, so that could be thought of, running through what you did when you were connected to the world, just in simulation. But the astounding thing, there's also so-called pre-play, where you see activation patterns in hippocampus that you will later, once the animal has learned to navigate in the labyrinth, you will see the same sequence that you saw when they were sleeping before that experience. This is certainly astounding. And so that hints that the machine that does the sequence is actually fixed. And when the animal navigates, it associates that with particular events out in the world. And so the sequence that you're seeing is really that fixed sequence that the hippocampus circus has at its disposal. This is not far from proven. This is just a thought. And I don't follow that literature so closely. I don't know exactly where that stands, but that could be a possible neural substrate for this. Hippocampus would be a very good place for this because hippocampus is famous for being connected to so many different cortical areas. So this idea of having enough neural substrate to link up through Hebbian learning to the contents of your sequence makes some sense. Good. So that's the three principles of how you select them. So let me show you this architecture that illustrates all of that. It's the same sort of thing. It's essentially a modern version of Julia's wandering robot. And this was done by Jantje Kulve with a visitor we had at the lab. And we published that in Neurorobotics. It's the this is the architecture. I'll show you that in a moment. Let me first explain maybe the task. It's analogous to your assessment that you show this robot colors in a certain order. This is simulation. And then you arrange these colors on the table in a particular way, and the robot, in this case, points at the different targets. So this takes away this whole issue of navigating and mapping and estimating where you are. This is all based on representations that where you know where you are, and it's much more closely associated to the visual representations. You will see again tomorrow when Raul presents that, or that are already presupposed in these grounding examples. So if you look at the architecture, it has essentially a form of scene representation that you build a simple version of, right? The camera, again, color based. I think we also had maybe only color, I don't remember. I think we had only color as a feature dimension, very simple. So you have these color space representations, and assemble again a working memory of that. And so that's where the contents lies. And then you have a movement architecture where you have a project, I believe, on that some of you might be able to do that drives the arm to a target that you have selected. So the target representation would be informed then by the scene memory. And up there is the serial order machine. This is the serial of these ordinal nodes, and these are the memory nodes that always activate the successor. And that machine would be informed about color, the color that is subscribed, the concept of color, and the color that then influences the motor behavior. And you would have a phase where you learn, that is, you learn the projection onto a particular color that would be then based on the color that you're currently attending to in the learning phase. And then in the recall phase, you would be exploiting these plastic connections to find out what color you should currently direct your attention at. And so here's an example of the learning. So the different ordinal nodes are, the color code is associated with which color they end up being for. So for instance, node number 1 was active initially, all the other nodes are subthreshold. When the object that's green is presented, and you have to, again, you have to see it's only saying object, you have to have detectors that detect that something changed is now in the visual array or is removed from the visual array. And the color is greenish here. And then the learning establishes the weight between ordinal node number 1 and this green color. And the fact that this is turned off triggers the offset detector in this frame. And that switches, that makes a condition of satisfaction for the previous state. And that switches now on the next node, the node number 2, which a moment later is, this object is presented to it. And that will lead to learning that connection between the second node and blue. And again, the offset of this blue triggers the transition to the next node. And here it actually takes much longer for some reason for the learning to saturate here and so on. So that's how you learn. And you doing this here at the bottom is really using Heppian learning between the ordinal node and that the particular color representation. This is how this model builds the scene. So you presented the system with a scene like that. This is analogous to what I showed. Did I actually show that? Well, I guess with what you, I don't know, did you actually do that? No, you didn't. So you will be, some of you will be building a system like that. So you're seeing the scene here, the salience. And in the scene, the system is actually sequentially selecting objects. So it's selecting here the pink objects. That will be this intention that shows there is a intention selection. So that's the perceived color. Here is your memory stack in which there are these columns at locations at which there is some input. I guess this broad one must be the arm, and there's some way to deal with that. Its color being ignored. And so now your attention is selecting this, and what you then do is you put this into working memory, and that so there's a peak being formed here. I don't know exactly at one. I think here at this column, the intersection of this color slice with that column makes an entry here. So you commit to your scene memory that at this location there is a, what is that, a pink object, and the color match field is sensitive to whether you're extracting the color that you stored here in the memory representation of color, and you're essentially looking if this color matches the color you're currently attending to. And when that's the case, you have a match, and that enables you to suppress that attentional selection, in the visual return, make sure that you don't select it again. So this happens here. This is when the condition of satisfaction. This is an example of a condition of satisfaction of a mental state, right? It's that you've entered it into the right thing into your visual scene memory. It's not a physical state. And that then allows the system to select the next item, which will be, intentionally will be this item here, just based on salience. And again, you have blue, and you select the in memory, I don't know, it's this one here that is selected. So the memory is put in here. You have blue in the memory that matches the attended blue, and you fire the condition of satisfaction, and then ultimately select some other item. I guess must be the green one. That's how the memory is built. Again, it's using these mental sequence. And you see it takes a similar amount of time, because this is now really just the time to build the peak and detect the match. And that is somewhat reproducible, but it doesn't have to be if the one peak is more intense than another, or there's some peak nearby that has some inhibitory influence. It takes a little longer to build the peak. All of those things would be stabilized again. These are these subtleties that in a lot of more schematic neural network thinking people don't really look at. And this is now how the sequence of actions is generated. So now you're recalling from memory, so activating the first node, then activates the corresponding color, which I guess must be green here. And that extracts the color position of that node, and that drives the arm to that node. And there is a position match field that creates now the condition of satisfaction for the reach, where you find out if the arm is close to, it's actually based on motor prediction of where the arm is. It's not visual prediction, I believe. And when there is a match here, that creates a condition of satisfaction for having achieved this, which inhibits all these nodes. And then the next node comes up, the second node, which is associated with the corresponding color. So the second node, I guess, comes up here, and the color seems to be blue. And you select the spatial position of blue and reach for blue, and so on. So then that's how you make the sequence of actions. Here, it's actually maybe not entirely visible, but it does take different amounts of time depending on how far the targets are. There's a cool demonstration of this on the next slide. This is a case where the same association has happened. So green is first, blue is second, and pink is third. But as the robot reaches for blue, I think, is it? Yeah, for blue, like here, the blue target is just made to jump. Sorry, I clicked on something. So the blue target jumps from this frame to that frame. It just jumps. So we just make a jump in the visual array. And so now the robot does not actually get a match. It doesn't actually reach the target. I think this must be here in this situation. And that triggers a correction movement, because now the new target is the new target is detected. The scene representation delivers the new target, and then it makes a second movement. You see that here, it's like light blue is the motor intention. I didn't explain exactly. It's an oscillator that makes a half cycle. It's actually an active transient that makes this movement here. So usually there's just one movement per each reach, and here this failed, and therefore is a second movement, correction movement to the target, and only then do you find the condition of satisfaction and load the next color. So here you see this is a longer trial because there had to be a correction movement, and the system doesn't forget that it is still working on the blue target, right? That's the core idea of dealing with in an embodied system with serial order. Right? That's really cool. As far as one can get excited about slides like that, curves. Okay, so I hope I got these 2 points across, and that would be actually all I'm going to say about sequence generation and serial order in a technical sense. So we're done with the technical part for today. So much faster than yesterday. Happy to entertain any questions you would have. So if you don't have questions, I'll move on to the more discussion section. So first thing I want to address is neural architecture. We'll talk a little about them and talk about 2 things: dynamical structural stability and non-synesthesia. Sounds maybe surprising. We'll see in a moment what that means. So what I want to make problematic is how we look at these architectures, right? You see the architecture just discussed, and we put the box here and say this is the scene representation, that's the serial order representation, arm movement representation, and then in there is the scene spatial selection field, and there's the working memory field and seance field, offset detector, right? So we label these different fields for different things. We say this is over color, and this is over space, and this is over end effector position and end effector velocity, for instance, here, and stuff like that. So why are we able to do that? So why can we label the fields with a function? And I'll also ask in a moment, why can we label a dimension? Why does it have that dimension? In fact, the fact that we do that has often led to misunderstandings, that people say, oh, this is like a computational architecture, and like you have the different parts of your code, like, you know, if you have a software architecture, then people make boxes, and they, let's say, this is the box for that, and that's the box for this, and these arrows then actually transport information. Like this box is a subroutine that computes some vector, let's say, computes the distance to the target, and that information, the distance to the target, is handed on to the movement generation box that does something. And you say, oh, that's computation. And we say, no, it's not computation, because it's really just one big dynamical system, right? And so these labels we put on the different fields and the different groups of fields are just for us, the designer and analyzer, to help orient, but it's really just one big dynamical architecture. So it's not an information processing architecture. That is, these different boxes are not defined by the input-output interfaces. It's not defined by this. One gives this kind of message and that kind of message, or this one returns, this function returns, you know, this information, and that function returns that information. In that picture, you have encapsulation as a way of making sure that only the information that is in the architecture that is on these arrows is being handed on, and that there is no under the rug or hidden passing of arguments from one box to another, which is one of the principles of sane programming, object-oriented programming. So that's not what we're doing, right? It's just one big dynamic system. So we have to ask ourselves, why is that possible? Why can't we do that? And that, I mean, it depends on how deeply you think about that. If you see that there is a question here, and it actually turns out there are 2 questions, one of which we've ourselves sort of struggled to really put a finger on. So one question is, why can we describe the dynamic function of these different subcomponents of our architectures in a fixed way? And dynamic function is ultimately what we call the dynamic regime. When I say this is the scene memory, then I'm talking about a field, for instance, working memory, a field that has that dynamic regime of being able to have sustained activation. Or I have a field, you know, that has a single peak feature, and so it is in that dynamic regime and can therefore do selection. Or I do the match, and I might have, for instance, a field that can bring long-term memory back into reactivate memory, so that has the boost-driven detection instability, for instance, and isn't that dynamic regime and so on. And so why do we have to worry? Is it clear that if we add that field to the architecture that we're still in that dynamic regime? That is something that when you tune these architectures, you're concretely confronted with, because as you add components to the architecture, well, something could happen for you to no longer be in that dynamic regime. So I'll address that. And the other is, why is it reasonable to still claim that the fields are defined over some feature dimension, even though they're connected with a lot of other things? So how are we sure that this field still, directs movement in this direction, or this field still represents this kind of color, or this kind of concept, when it's in this larger architecture? So the first question has a clear theoretical answer. It's essentially the concept of structural stability. So structural stability is the persistence of solutions, or the invariance of solutions of a dynamic system, when you change the equation a little bit. If you think of the parameters of an equation, then they would be continuous, for instance, and you would be moving the parameters around a little bit around the current value. And then what you want to guarantee is that the solutions also depend on vary a little bit when you change the parameter a little bit. You would say there's only a continuous change in the solutions when there is a continuous change in the parameter. And you could, I already argued, I think, on the very first day, that when you have an attractor, that an attractor is also structurally stable. That is, when it's stable and you now change the dynamics a little bit, it will not become unstable, and it will only shift around a little bit. And if the ensemble of attractors is stable, then actually the entire flow, that is the ensemble of all solutions, is stable, or is not stable, is invariant, in the sense qualitatively. It might change a little bit, but it will be continuously depending on that change. Of course, when there are bifurcations, dynamic regimes involve not just attractors, but also their bifurcations. Mathematically, you can actually include that in an attractor description, because you could say that I read down the entire bifurcation diagram, and I include the parameter that takes me through that diagram in the dynamical description. It will be essentially a marginally stable dynamical variable, the parameter itself. And then you can still talk about the structural stability of that. So that's an argument. That's why it is possible to keep the dynamic regime invariant as you change the equation. Now, when you enter a field or a set of fields into an architecture, that's like changing the equation, because you're adding new couplings. Let's say they were already there, but when there is a non-zero stuff flowing through these connections, right, then effectively the equation is changed. So being part of an architecture is sort of like, and something happens somewhere else in the architecture that is like changing the equation a little bit. So the attractor dynamic property is critical for what we call dynamic modularities. That is, there's a possibility for the fields to retain their dynamic regime as activation elsewhere in the architecture changes. This is a big deal. This was actually a big problem with analog computers. Analog computers had that very problematic feature that when something in the high-dimensional state space of those changed, it could affect any other variable. So they were very difficult to program and to tune. And digital computers are so much superior, because in digital computers, the individual elements of the circuit, right, are not these complicated time-varying oscillators. The analog computers were sort of big oscillators, essentially, or ensembles of oscillators, while the flip-flops in the computer are bistable elements, just like our detection stability. They're bistable, but at a microscopic level. And that bistability makes them robust. That is, any individual flip-flop in there is not affected by the state of all the other flip-flops. And that fact that it's not affected is ultimately mediated by its stability. There's some physical radiation when the transistors get very close to each other in these very, very microscopic circuits we have now. You're hitting the limit of that, and you do have to make sure that that remains true. And that's how the individual pixels are independent physically of the other ones, and therefore you're able to independently vary them. And therefore, in that system, that's a modular architecture. Now, here in our language, it's of course not these microstates. It's not like we're building this from flip-flops. It is the macrostates of a whole population that is stable and has functional meaning. And but the principle is similar. You know, we're creating stable states and maybe bistable states and the dynamic bifurcation regimes that we make structurally stable. Now, unfortunately, structural stability is a infinitesimal concept, right? It's that around the current state a little bit. The mathematical theorem about that just talks about there is an environment of the parameter value, but just see how large that is. There exists an environment within which there is no change, no qualitative change. But in practice, of course, your change could be beyond that, right? And so the parameter tuning that some of you have to do, even in the projects, have to do with that fact that even though in principle, so what the theory just says, there is a parameter regime where the properties are invariant, but it's still sometimes a problem to actually concretely find it. And so that's not so easy. That happens especially when you're connected to sensory inputs in some other form. Is a problem on the motor side, because these sensory inputs might change in amplitude or amount, total activation, and that can make macroscopic changes that are not infinitesimal enough for your dynamic regimes to be robust. And it's a real interest that you then develop in doing some kind of normalization on the inputs. The fields themselves do normalization because the peak sizes don't depend so strongly on input. You see that actually here, that this input and that which separates two dynamic regimes are very no, that's actually the wrong argument. But the peaks are somewhat invariant under variation of inputs. But it is still work to tune the architectures, but the property of the attractor dynamics in the bifurcation makes that it is possible in principle to do that. So that's the answer to this dynamic challenge, the dynamic modulation challenge. Why do fields retain their meaning? Why is it true that a field is about color, even though it might in the architecture, receive inputs from all kinds of directions? That is not something that is automatically guaranteed. You could build a neural architecture. You can do that in CEDA. It's very stupidly where you provide to the architecture color input, and then you also wire it up to a microphone so that it is also defined over pitch. And then you would get synesthesia. That is when you would hear a sound of a certain pitch, you would also see a certain color, because somewhere else that field that is over color and or pitch would be, for instance, be connected to color concept nodes, and you would be activating your word red because you hear that sound. That is synesthesia, and there are actually some odd phenomena where some people do have things like that, where color is invoked when they hear something, or sometimes across like smell and touch, things like that, and it's considered a problem, non-normal state. And so it's exceptional, and it's exceptional in the brain, because essentially the answer we have to that is that it doesn't happen, that your brain is not wired up that way. In your brain, there is some kind of unique track that is, if you think of sensory field that is relatively far from the sensory surface, it's still true that there is a unique path that for that field to represent some perceptual features, and similar on the motor's end, and similar on the concept among each other, so that things don't get mixed up. And that is not so that's an additional constraint on our theory. That constraint, so that would be the analogous idea to encapsulation, some kind of modularity that would be clear. So the connections between the fields only provide activation from one to the next, right? Sigma of activation, no contents, right? So the content just comes from who is connected to whom. That's where we're just called connectionists, right? It's who is connected to whom that determines what the meaning of that activation is. And the encapsulation is that meaning is preserved, that is always, that there are no projections in the architecture that could change that meaning. So the brain is very special, so it doesn't do these sort of things. So even if you were to make a random brain, it could do such things. And so we would say, well, that is actually an outcome, an evolutionary outcome. So our brain is special. We know it has this particular array of sensory areas, motor areas, and then these are the spatial areas and the more contents-oriented areas like IT and frontal areas. They're more about control. They have these specific functions, and they are systematic. There's a systematic way of how they are wired up to not mix up the contents of these representations, right? That's really our argument about that. Good. So that's a bit abstract point about architectures. That's why it works. When you design the architectures, you're automatically using this principle unconsciously, and you're working very hard to make this principle work. Good. The last part of this lecture is to expand a little bit the ideas that were just mentioned already, and again, position the whole framework more broadly in the literature. And this is something where many of you, I think, are relatively young in your career. And so I don't know how much you know about connectionism, about classical cognitive architectures and other approaches. So I'm just throwing this out there, and maybe different. Some of you find that perhaps inspiring, others learn on that occasion about other possible ways of thinking about the brain. Ideally, after this, we can discuss that a little bit to bring in your own knowledge. So I wanted to address 4 points. I wanted to return to embodiment and clarify what that is. Some people who study cognitive science, often with a philosophy slant, talk a lot about that, and not all of the ways people talk about that are consistent with how DFT deals with embodiment. Then I want to compare again to connectionism. I did that already a little bit as we went along. I want to deepen that. I want to compare DFT to symbol manipulation, classical idea of what cognition is as a form of computation. And then a more specialized comment on the other major proposal, how higher cognition could be done neurally in the so-called vector-symbolic-architectures. Good. So first, let's talk about embodiment. So I originally talked about embodiment in the sense that simple sensory motor behaviors actually contain a lot of cognition. So for instance, when you play soccer, you do things like selective attention, sequences of actions, maybe even planning, predicting things, deciding things, keeping in memory things. For instance, you're not making a visual search for the ball every moment in time, right? You're using your memory of where it last was, maybe even predict where it's going based on its last estimate of velocity, or maybe you make even a prediction about the other players, and you have a scene memory, and you actually also have intentions and goals, and so it's, maybe you have activated a whole routine, a strategy. And these are my kids when they were small, and now adults. I'm not sure they had a big time strategy. Yeah, but there's a lot of cognition in there. And then the argument was, well, in the way that cognition is done reflects that history and is connected to these sort of things. So that decision making in a soccer game isn't qualitatively different from decision making, I don't know, when you decide for a chess move, let's say, which is also a physical movement thing, by the way, or decide for, I don't know, for a certain decision when you program a computer. But there have been, sometimes people have pushed this idea to say, well, cognition is embodied because when you're doing cognition, you're always activating the motor system a little bit. You can't help that. Or there's always some sensory activation, like you're imaging things. So you see in, for instance, visual cortex or in sensory areas, you see some activation in the brain scanner, for instance, when people are thinking about those things. And so that has led to some debate. And I would say the upshot of the debate is that does happen, but it's subtle and it's not really necessary. So it's not true that you can't think if you're totally sensory deprived. I mean, that does make you unhappy, but it's not really a qualitative thing that then you can't think. And there are these subtle motor effects. So if you are just thought about an action then doing an action that is compatible with that can happen faster than doing an action that is not compatible with that. But these are small effects, and they can be overridden, and so they are not necessary. They are signatures, perhaps, of something that I will claim in a moment, but they are not really. That's not really what embodiment is. These are sort of side effects of embodiment that are maybe interesting, but not constitutive of embodied cognition. So our view of embodiment is, in a sense, more abstract. It really says, well, it's the same neural principles that apply to cognition, because cognition emerges from the machinery that we have that has a sensory motor history. And these principles are from, about continuous time, about stability, about closed loop, intermittent links to the loops are intermittently closed. For instance, you just saw sequence generation. There's a moment when the loop is closed, but then there's another part of another cycle where the loop might again be open. And stability is really overriding the big issue there. And so this postulate that embodiment means sharing the principles of sensory motor, that higher cognition shares the principles of sensory motor, is a more abstract view. That is, I would say, what could be argued for on an evolutionary and developmental basis, because cognition comes from the same brain that evolution does all the sensory motor. It's actually only gradually becoming more abstract in evolution, and the same actually in development. It turns out that in development it's initially very sensory motor, and that then it's an achievement to become less dependent on the sensory motor. That's sort of an explanation of why that makes sense, right? So that's a little bit more nuanced view of embodiment than sometimes argued. And I can talk more about that, but let me maybe just put it out there. The second point I want to make is about DFT and connectionism. So connectionism, neural networks, of course, this presupposes that you know roughly what connection is. And clearly, dynamic field theory models are neural networks. They are use a mathematical formulation that is not totally common, but that is not exotic. This is a survey over possible or existing neural networks in a review article that Thomas and McClelland published in the Handbook of Cognitive Modeling, I think, in which I wrote the chapter on dynamic systems. There's a new edition of that book coming out actually this year. And so I would say we're in there, right? Attractive neural networks is a very general term. They don't exactly pigeonhole us, because we would have be a subclass of these. And they say it's competitive neural networks, and they mean only the feed-forward part, even though it really should be also recurrently looked at as a recurrent network. So we'll be maybe somewhere in here. So we're, in that sense, just a subset, subfield of connectionism. But and we share with connectionism conceptual commitments. So, for instance, I mentioned that initially that we're thinking of. Sorry, I have another slide with the shared. Oh, I deleted that slide, perhaps. Yeah, I deleted it. Oh, I have it on here. Sorry. Shared is this level of description activation sigma. That's what I mentioned initially, right? That we're not doing the spiking, so we're having a shared, more macroscopic picture. Now, in some way, we're more specific. We're sitting on a subset, and that really means we also think that's important, and we're not doing everything else that is also allowed in connectionism. So, for instance, we really think that functionally significant state should be stable, and that's not shared across connections. So some people allow transients and even marginally stable states and so on. And we're really postulating that it's populations that are the level of description that is sometimes just not discussed in connectionism, sort of implicit, but some networks are sort of formulated as if you had, for instance, grandmother neurons, or as if it was the precise pattern of activation across precise population, individual neurons that have significant roles in the population, where we will argue that it's really population is sort of an averaging system as well. And of course, we emphasize the instabilities, which is really pretty much not done by anyone else. So pretty much anyone else doesn't really pay attention to that. It's not quite true. For instance, I would say the people who do these hippocampal place cell computations share that too. They just don't make a lot of fuss about that. And because they have they're a bit more reductionist, they often think about the relationship to the theta rhythm, sort of implementation detail, one would say. So but they're close. Now, there are some ways in which I would say, we're also really differ in our commitments from the connectionist commitments. And the most important one is this question of localist versus distributed representations. There was actually a debate in connectionism early on, like in the 80s. I was just entering that field about that, where all kinds of arguments, and you can still find some review articles that go back and forth about that. We are clearly committed to localist representations, and the reason for that, so localist representation really means that within the neural network, the meaningful states are states that are localized in the neural network, for us localized in the field, for instance, right? Now, there can be, I'll mention in a moment, the binding thing means that you can have multiple localized representations, but they're all localized somewhere. And that somewhere has to do with the interaction, right? Because the thing that makes our state stable is the regular pattern, the homogeneous pattern of neural interaction, close, local excitation, global inhibition. And it's that homogeneous pattern of activation that gives the fields or population or different dimensions that representational power, because you can represent just about any peak, even the peak you never created before, but you have the substrate to create these continuously many peaks. And I contrast that again to something like Hopf neural networks, which also can create a lot of attractors, but only the specific ones, because you have to have specific weights, not these regular weights, but some specific way. Each neuron has to know which other neuron to excite and which other neuron to inhibit, and therefore it can only represent memorized stuff that you've learned. And it's actually also very difficult in fields like that to make a targeted instability. If you're sitting in one of those attractors, you can make, like globally, you can just blow up the whole thing. But it is difficult to say, I want to deactivate this state and activate another state. And that capacity is linked to the field idea that goes back to Wilson-Caron and Amari and so on. And once you have that field idea, the scaling arguments I gave you imply that these fields have to be low dimensional. So in a way, we're committed to saying all cognition is based on these low dimensional localist representations. That's a very strong constraint, right? That really means that when you do cognition, you only have these, one could even say it's somewhat crude, right? A low dimension, you just remember color, orientation, a few features. And that's the sort of thing that you do. And by autonomous, I mean, that's the kind of cognition that you do that's not really driven by inputs. That's what you can do with your eyes closed. That's what you can eventually image or drive purely cognitively. It's a strong constraint. So for instance, I would say the high resolution images that you have, that when you look around, those are only possible when you actually get that sensory input. And what you have in memory when you close your eyes isn't like that. And in fact, that is a psychophysical phenomenon that you don't really know the details that you think you know based on your impression of the environment. You can answer a lot of questions by looking there, right? But that's when you get the sensory input. So that's what I mean by this phrase autonomous cognition, cognition generated within the nervous system, not driven by sensory inputs externally. And pretty much all thinking is autonomous, right? So, just think of as a cat, the actual visual input you have is quite different from the scene that you think you see. So that's a strong constraint. It has one positive side effect, as I mentioned, that the memory trace can play this whole role of reactivating prior patterns of activation. Of course, it's not reactivating all the detail because it only has that low-dimensional representation, but it can re-instantiate that. So it provides the theory of memory, and there's actually not the theory of memory, a neural theory of memory is actually still missing. People in the hippocampal world are working hard on arriving at that. They look at very special subcases, but that's certainly a feature. And that's, so far, I would say, largely consistent with this thought that the actual condition is this low-dimensional stuff, and nodes being, of course, also very, I'm thinking of nodes also as parts of low-dimensional, right? And another implication for that is that it actually gets, it's really different from distributed representations, right? Distributed representations, when they are really sort of at the level of the individual neurons, have no place in this picture, right? Except maybe as models, complicated models of memory, of long-term memory, but not very easy to operate on. So those of you who are primed or know something about connections might know that the Rumelhart-McLennan model, which is here reproduced from a much later review article of McLennan and Rogers, was sort of one of the prime examples. That was the original idea of having distributed representations, in the sense that a certain concept was just the collective activation of many different attributes and maybe some relations, and including perhaps some hidden nodes that were needed to make these selections, and so that picture is one where, so it's distributed in the sense that there are neurons that contribute to one concept that also contribute to another concept, and that it's the particular pattern of contribution that makes out one concept, and therefore you get all these effects, essentially associative memory kind of effect. That is, you can, for instance, do pattern completion. You can say what is missing from a particular exemplar, or make predictions based on that. You can do also, of course, auto recognition and other things. And you know, the German-speaking among you might know the Steinbuch's Gedächtnismatrix, so this idea that the brain is a matrix, operates like a matrix computer, so that you can put a vector in and find the column that best matches that vector. That will be association. And so this picture that we're using would say, well, that kind of association that is based on high-dimensional vectors and multiplication, that's not how cognition works. That's not autonomous cognition. That happens perhaps, and I'll say in a moment, maybe in visual perception, but it doesn't work in the brain for anything higher. So certainly not for concepts like this. But you could see perhaps that these sort of representations, as claimed here, they're actually at a rather high level, right? These are all concepts, right? Grow, move, petals, wings, I don't know, is a, with the relationships and so on. Those would be things that we would call conceptual representations, and Daniel will tomorrow expand on that. And we would represent those as perhaps multiple localized distributions that are bound. The binding is in the way we did through space, or then through label. And therefore, each individual subpopulation, so each of those would be a subpopulation that would be localist in that sense. And you see it's somewhat localist here along these different feature dimensions, right? Because they are actually significant that they're using a localist picture for these components. And so this whole pattern, that's a distributed representation, but in that sense of multiple bound, in our sense, bound localist representations. So the dynamics could stabilize those. The price you pay is that it doesn't have that property of matrix memory, of association. Not automatically. I mean, you have to build that, not just play this idea of vector multiplication, scalar product among vectors. The one exception for this would be, of course, the high-dimensional feed-forward neural networks that come from sensory surfaces, ultimately. So Raoul Griebmann will tomorrow talk about his modeling, where he takes a deep network and then maps that deep network onto ultimately some low-dimensional representation of our nature, where one of those axes is sort of a label or index axis, so categorical in nature. And that's, again, localist, where peaks appear and so on. And so there's an idea that that you would have these high-dimensional fields. They do exist in the brain, but that those are really good for essentially classification tasks where the high dimensionality serves to be highly discriminative, to be able to make fine distinctions and solve difficult classification tasks, and maybe a couple of other tasks around that as well. And these are all tasks that are characterized in response to input. So you need the input maybe as a volley. You don't need it perhaps sustained, but you need it to, as a volley, to go through that system. And in response to that, it would ultimately make a compressed representation of that. And then any autonomous cognition where you make inference or think about it and keep it in memory or whatever you do, that would be, again, in a localist representation. That would be our hypothesis. So currently, a lot of these deep neural network models, even the end-to-end models that act based on sensory information, they're acting, their inference and so on, not neurally. They have some algorithm that reads out a maximum or has some probabilistic rule implemented on the outputs of a field. So we would say the outputs of those fields, that's when neural dynamics starts. And it would be typically a neural dynamics of discrete nodes, for instance. These labels, in a sense, are discrete nodes. Actually, not quite, because there are some low-dimensional features still associated with outcomes like that, and one of them is space, and I'll be talking about that. So that's one form of positioning ourselves to connectionism. This last part is still not so deeply developed, so we're just working out how general this is, and Ron was one of the people who pushed that forward, and Daniel starts to think about these issues. Finally, this second last point. How does our theory relate to the more classical approach to cognition that's based on symbol manipulation? So you're all young, younger than me certainly, and so in your lifetime probably nobody seriously thought that the brain is exactly like a computer, or a computer is exactly like the brain. In the 1970s and 80s, if you open the textbook on cognition, there was that idea that cognition is a form of computation of symbol manipulation. Actually, people would really say cognition symbol manipulation, and the brain was just one special instantiation of a general principle of general intelligence, and the brain now would be using the neurons in terms of hardware, but its core function would be symbol manipulation. And so I don't want to review the entire history of thought there, but let's say if I condense that down to its core, then there are two ideas in there. One is the so-called information processing perspective, in which cognitive functions operations are essentially function calls, right? So for instance, the things we discussed, like something being to the left of something, would be a function call where you insert the target location, insert the reference location, and the function returns, for instance, yes, if it's to the left of, let's say, a Boolean 1, or a Boolean no, if it's not to the left of. That's a possible way to do that. So that's at the core of classical architectures. It took here something from Act R, one of the most developed cognitive architecture that's still used in a lot of, for instance, in cognitive human factors work. It has that inner structure that is the contents are symbols. For instance, they often use mental arithmetic as a working horse, and they would have what they call, additional chunks of information. And there's an addition fact, for instance, when you do mental arithmetic, that would get an argument like 8 and another argument like 12, and then, I don't know, actually, I guess 2 of these are summons, and then you're supposed to return so when you have the 12, you can say whether it's true or not. Actually, it's kind of interesting that the contents is symbolic. And it's these, they don't really worry about the neural representation. Say it's this information that flows on these arrows, but they also have activation and weights, and the activation and weights are actually to organize the process, to, as they say, to fire a rule, a production rule, to make a production, to make a computation. So unlike in the computer, where this would be all based on just the addresses of the locations that are mapped, given to the CPU, here it will be based on these neural things, the activations, the weights determine the activations that will determine which of the chunks is being operated on. But the contents, what it's actually doing, that is really symbolic. And I'll comment on that in a moment, but just to represent that. And then the other element of that is that the sequence of such rule firings and evaluations of the contents and so on, that is driven by a computation cycle that is outside the neural metaphor. So in ACT-R, for instance, there is a hypothesis that you have like a 50 millisecond cycle of these things happening, and some kind of hand-waving about whether it has to be precise or not, or synchronous across the brain. But essentially in these architectures, there are these sequences of steps where you load in the arguments, and you select an action, and then you pass that on to someone else, and all of that is on a rigid grid, essentially like a function calling on a computer, where the function itself indicates when it is done, and it provides the outcome. It's not quite true. They are actually exactly about thinking about how long it takes to fire a rule that is sensitive to these activations. So you can account for certain psychophysical effects about taking longer or not, but the sequencing that you say, now this rule is fired, now I'm doing the next one, that is outside the neural metaphor. You're not actually accounting for how that happens. And so in DFT, we are aiming at these sort of things, right? That when I said higher cognition, it is about achieving this form of flexibility and invariance and abstraction. But we're doing it differently, right? We're doing this thing that's described here as function calling through the combination of attention selection coordinates forms and the sequential processing that I explained today. So when I talked about how you can direct input into a target field, reference field, and then find out through a coordinates form what the reference-centered representation is, then you can activate a node that's to the right of you. Effectively doing that, you have very fixed. So it's not an arbitrary thing I can put in here, and don't put coordinates in here, but I have arranged this neural network so that certain kinds of inputs can specify the target, and certain kinds of inputs specify the reference. So it's much more constrained and actually costly. You need a lot of neural infrastructure for that. The coordinate transforms are very costly. But then it does actually realize neurally this sort of thing, right? The coordinate transform does this kind of function calling. The upside of doing it this costly way is, rather than, let's say, just take the contents along with you're saying activation reference, and now the coordinates of the reference object, I just have that as some contents that I can pass along. And the advantage, of course, is that it's grounded, right? That we can actually really link the contents to sensor inputs, like we can point at the object, we can visually attend to the object, we can extract its feature values and so on, or drive action ultimately. It's also very natural to link this to actual neural forms of learning and neural forms of memory. A lot of these models actually have memory, but the memory consists of some kind of storage and something that's not really being accounted for in the neural framework. So that would be saying that we are aiming at achieving something like this function calling stuff does, but in a much more neurally constrained way. In that sense, it will be a neural account for how that kind of symbol manipulation happens. And the second aspect is, of course, what I talked about today, that the sequence of processing steps really emerges from that same system. So it's not done by some extra mechanism outside. It is really the dynamics of the activation, the targeted instabilities that do the sequence processing. And that would buy us this robustness under embodiment, that you can actually act out those things. And in ACT-R, that is being attempted right now. That ACT-R architectures have some sensory motor modules that you can plug in. But this property of, for instance, being able to sustain inner state as input changes, and to not be susceptible to distractors, but still open to switching, that's not something that's solved now. So in that sense, one could actually perhaps think of DFT as a possible neural approach to that form of higher cognition that symbol manipulation was aimed at doing. And that's our research program. So Daniel's work tomorrow will be pointing in that direction, for instance, and we're very actively working on things like that. Yeah, that's going to be our problem for the next 2 years, perhaps. To sometimes people talk about neurosymbolic approaches. We could say, well, we think DFT is the ultimate neurosymbolic approach. The symbols don't have to be grounded, and so we don't even talk about symbols. It's just the emergence of the cognitive properties. Last comparison I want to make is with VSA. It's a much more specialized topic that maybe not everyone knows. VSA goes back to Smolensky at the very origin of connectionism in the early 90s. He proposed that vectors, it was important that they're high dimensional, and it was thought that the activity of a lot of neurons could be thought of as one big vector. And so these would be vectors of, let's say, of 0 and 1s, if I think of firing, non-firing, or some real numbers. That these vectors could be the symbols. That is, a certain firing pattern of the neurons in the brain would be one vector, one symbol, and a different firing pattern of those neurons would be another symbol. So you can see this would be a way how the neural substrate can give rise to a lot of different symbols by just changing the activation pattern. Would be really distributed, very attractive. And Smolensky worked out, and then there are a couple of folks, Ross Gaylor, with whom we interacted quite a bit about these things, and someone called Konerva, and someone called played that, a different version, of these. Now this button doesn't work anymore. What's happening? Oh, my keyboard stopped working. The different versions of that, and I can't explain that fully. They have a special method of how they do things like binding and function calling. So this is like information processing, because they arranged ways how you can hand these activation vectors on from one part of the architecture to another. Now, the main criticism that was raised very early on and has always been in the background is that that's not nearly plausible. It is actually not clear how in the nervous system you could keep a population of neurons firing in a specific pattern without input, and how that pattern could then be transformed to another pattern, without specifying that other pattern by input. So these operations written down here, they are mathematically, you can do that, write down these vector equations, but there is no way how a neural network can actually do that. And it's, again, a stability issue, how you keep the neurons from diffusing, everything's firing, or also from decaying. Nobody's firing. It also has a principal problem in that it still has simple grounding. That is, you still have to say, how does a vector like that arise from sensory input, and how does a vector like that lead to a particular action? And there are people who are trying to work on possible ways of that happening. So I'm not saying that as such is a reason why it couldn't be true. Now, in the last couple of years, there's been quite some excitation also through the very skillful publication policies of this group. Chris Eliasmith is the leader of this group. He developed in his thesis work something he calls the neural engineering framework. And the neural engineering framework has a funny name. Essentially uses integrated fire neural dynamics and shows that you can essentially encode pretty much everything in that framework. So you can essentially, it's like a numerical implementation of any model. He even showed that you could take a chaotic dynamic system like a Lorentz attractor and make a spiky neural network version of it with the integrated fire neuron. And so there's been the idea that using this framework, you could find a neural implementation of VSA. And that is being discussed as a possible neural way of dealing with symbolic computation. So NAIF as such is actually totally model neutral. That is, you can take any model, now with some certain constraints, and implement it in Naive. In fact, this group and some other people have taken DFT models and implemented them in Naive. You can just do that. It's some work, but you can do it. I'm not explaining in detail. So as such, this doesn't yet mean anything, but that would open the possibility to say that maybe I could take a model that is not so plausible neurally, like the VSA model, and then make it plausible by using this neural engineering framework. Now, there is a particular problem with that, I believe, but again, this is under debate. I just discussed with one of the pioneers of this approach, Terry Stewart, that idea very recently. So there's a lot of criticism one can make, but this would be one possible criticism. So what happens in this approach, it's very interesting. You have these, so you have the underlying vectors X. So in the underlying space X, there will be an abstract vector. You want to do something like mental arithmetic. You want to compute X squared, or the square root of X to the power of 15 or something, just to make it concrete, right? And now you want to do that neurally. Right? And because we don't have function calling, what we'd have to do is have a neural network that takes that X as input and can compute its, third order, third square root or whatever, irrespective of what X is. For any X, it could do that. For any random of these high-dimensional random vectors. And the way that Naive does that, which is the attractive part, is that it has limited neural ensembles, so not as many neurons as possible vectors X, but some subset. And it just needs to connect these neurons, and they can then do the symbolic computation that you want to do. And the key criticism is that if you look into that, there's some kind of hidden magic here, because you could imagine if you're representing, let's say these neurons represent X squared, and these neurons represent X, then how can you do that? How can you make these neurons square whatever is here? Right? If that whatever is here is some code, some complex code. And it turns out you can. So what you need to do is you need to have an encoding scheme. That encoding scheme would say a certain symbol out there, X, is now represented by this population of neurons by their tuning curve. So they are sensitive to a particular pattern of inputs, which makes that now when they fire in a certain way, then that means X is currently presented. And it turns out that if you now want to compute the weights that represent X squared, you have to figure out that weight, you have to actually decode, that is to extract again what X was there, and then re-encode that, but we're now re-encode X squared. A fresh population of neurons, but these connections here do effectively the decoding and the re-encoding. And the mathematical theory actually does that for you. There's a software that does that for you. And that is, it's okay if you're just aiming at a numerical implementation of this in spiking neural networks, but it means that it's actually not. They say it's like it's a ready-made brain. You're building a brain that's already done. It's not a model of how that could be learned, for instance, and that's important because when you were to learn that, that would mean that if you go across a whole number of steps, that even connections far from the original ones still have to know what was encoded originally to decode that and re-encode the correct thing. And that non-locality is sort of a hint that something odd is happening. So that's one could seriously doubt whether there is such a universal trick, that is, that you can just write down any computational machine and then say, by using Naive, I can translate it into a neural population that fires, and that's how the brain does it. That's a very daring hypothesis, and I think it's possible that it's really wrong, that it's not developmentally possible to build such a brain. It's not robust. But that's a subtle argument, right? And very few people have really studied Naive well enough to really fully understand that. I believe we have, but no, I'm not saying that's the last word. But so this is a major competitor in a sense. People are looking at Naive, they call that then spawn. When they apply Naive to visual VSA, then they call that spawn, stands for something that I don't remember. So that's a more specialist. So those of you who don't know that, but you might have heard of it, or you will hear of it, and then you can think about it. Okay, though that actually really brings me to the end of today's lecture. I have maybe a little bit of a pointer slide, a outlook slide. So we've done a lot we do a lot more, of course, in DFT than I'm able to present here. You will see some specialized things in the next 2 days. And I just want to point to maybe 3 directions in which there is ongoing work that we're very interested in that are sort of fundamental in light of this claim that DFT could be the neural theory of higher cognition. So one is to go beyond these very simple examples of just having some relational concepts that are grounded and to really do things that are closer to what actual thinking is, and maybe also what manifests itself in language. So for instance, sequences of relational concepts that exchange arguments, where when you say that thing that was above that now also does something else, or the person who entered the door is now says this or that, and then you have to say pass the argument to the next phrase. And I funny phrase here I put here. And there is also some hierarchy. That's actually what is represented by hierarchical structure in syntax, right? That you're elaborating a point that was previously made. So Daniel will show tomorrow some of our first efforts to go in this direction. It's a big challenge because we always require a lot more machinery than well, that's the question, than whom, but it certainly require sophisticated machinery. A related topic on the motor side is being looked at. Sophie Erdker, who presented at the school last year, made some first steps in this direction. Stefan Seering was just joining us to develop that work further. So it's the same sort of thing on the action side. So how can you make more structured sequences of action that have some kind of interdependency and work toward goals, so that how to solve problems, how to achieve goals in the task, something that you very naturally do, not just in soccer playing. Toaster repairs, the example I was made. How that's also some kind of symbol representation, because it is at a conceptual level, but then you see the grounding because you have to connect that level to concrete actions and maybe the percepts that support those actions. And that touches on the third goal that Jan will be. So we don't have this year will talk in this direction because Sophie actually left our group, and we haven't built that up yet enough to do that. Jan Tjekulve will be presenting on Friday a little bit. The first steps in this kind of direction is so far from emotions and motivation. But it's this idea, how do you actually give or explain that a system does anything at all? If it's autonomous, why would it do anything? Why would it go somewhere, right? This is the intuitive notion of intention here. Why do you have intentions? Not the philosophical sense of that. So philosophical people would call that maybe desires. So Searle would call that desire. Why do you have desires or drives and these things, and how are they organized? And that plays into this here, because when you act, you have some goals in mind. It actually also plays into this because when you think, you have some goal in mind. And if you communicate, you have some goal in mind. And that is actually, as we know, linked to emotions, but we're very far from understanding that. And generally, neural AI is very weak on that. So it's very funny when people say that the new AI systems will conquer the world, but they have no desires whatsoever, no motivation, no drive, and so on. There's reinforcement learning is maybe the one little thing where they desire to have reward, but that's notorious for the poverty of that. Well, how little flexibility comes from that. So I think that's an open frontier, and I'm very interested in that kind of frontier. Good. This is as far as I'll push this today. We'll have these lectures in the next 2 days to expand some of the ideas and directions related to that. So I'll stop sharing and stop recording.